morning. Wonder if Aaron is around. See if I can grab him. Okay. All right. Well, I've pasted a link for Aaron, and glad. So we can go ahead and get started.
Yay.
All right. So last time we had looked a little bit more carefully at the transitions in the virtual machine in the linear types can change the blockchain. But what we hadn't done was to look at the type judgments, and so that's kind of useful. The main thing to take away from the transitions was just to understand, there were three takeaways. One was just to get a feel for the basic computational model. It's a little different than the pi calculus. It's a little bit more symmetric, and I actually found a way to unify that computational model with the pi calculus, but we don't have to go into that. There's a and the second thing is to understand how the namespace is constantly being kind of enriched. It's growing and shrinking. And so where computations live is kind of dynamically changing,
Right.
And to show that this can be done, fairly in a fairly straightforward fashion. And the third thing is just to get used to this kind of way of writing down the specification of a virtual machine. This spec is what is written in a format called structured operational semantics, which was developed by Gordon Plotkin. And most of the programming language semantics community uses this style for writing down writing down language definitions. In such a way that the language definitions correspond to a kind of abstract or virtual machine. So that's why it's kind of important for folks here to become familiar with that, because that's the sort of standard, the de facto standard. And
sorry, what was it? What was the standard called again? I want to write it down so I can.
Yeah, structured operational semantics.
Okay.
And there's some off-the-shelf tools that are really interesting and useful for writing those down. There's a tool by Peter Sewell called OTT.
Okay.
So that's actually very, very useful. And Mike and I. Mike Stay and I have been working on some results that will allow you to generate type systems from such specs, and fairly rich type systems. And so one of the things we've been looking at is, once we've got all of those results hammered out in such a way that we can communicate them to a larger community, the next step is to do it to write a tool which allows you to generate the type system from such a spec. And so the OTT format is a nice machine readable format. Hey Jeff, thanks for joining. Glad we could have you on board. And glad you're excited about the recording thing. Yeah, I think Wendell's idea is a great idea.
Is that OTT with 2 T's?
OTT, yeah, I'll get you a link. Hang on. There we go. And there's the link.
Oh, thank you.
Yeah, absolutely. Okay, so and let's see if I can find there was a nice paper by Gordon, kind of talking about structured operational semantics. One of the things that Mike and I have done. Yeah, here we go. I think this is the. Okay, so this is the original paper by Gordon, in which he proposes it. And if you look carefully at the functions as processes paper by Milner, you'll see that that's the first time we see it really utilized for the PyCalculus. Okay, so that's the original one, and then here's a and here's kind of some more modern research on the topic. Okay, cool. So you guys are so I just wanted you to understand, you know, to have experience with a system like this, and once you understand structured operational semantics, it's, you know, it really makes specifying languages much easier. I mean, basically, specifying a language shouldn't be harder than specifying a data structure. You know, so you know, a data structure that you might be, you know, very familiar with, but that is, you know, somewhat rich. Specifying a structured operational semantics should be on the order of that kind of complexity. Okay, so let's now. I'm going to do screen share, and we'll go back to the language and the little paper here. Okay, and now we can go. Okay, so we've looked at the syntax. We've looked at the operational semantics. I suggested that you guys kind of take a look at the intuitive example. We can go through that if you want, but given the limited time that Metallic has, I'd rather jump to the type system.
Mm-hmm.
So there are two components to a type judgment. I'll just take the very first one, which my mouse is on right here. Can everyone see that?
Yep.
Okay, awesome. So the components have to do with being able to relate programs to types, and the way we're going to read this in turn is the way we read these rules are essentially as if then else's. So above the vertical, the horizontal line, the dark horizontal line, is the if, and below the horizontal line is the then. All right. So this is the hypothesis up here, and this is the consequent down here. So there are some requirements, some type judgment requirements, in order to make the final type judgment. The other thing that we need is we need the types themselves. And so in this case, what we have for the types are effectively linear logic. So I introduce the linear logic above. So the types are tensor, which means, so if A and B are type specifications, then A tensor B means that whatever term you have has some activity in A, isolated with some activity that meets the spec of B. And par means that, let's see, where's par? Par means that you have some activity in A that is connected to activity in B. And similarly, so I think I may have, okay. There's a similar thing. So with respect to tensor and par, the main idea is that the sequence, the hypothesis that's necessary to establish A, or the resources that are necessary to establish A, are completely independent of the resources necessary to establish B. So that's the requirement of this type judgment. And if we look here, that's what's going on down here. So without having to jump back and forth, I'll just call out the type as we go along. You can kind of see the different the different types inside the type judgment construction. So these rules are called type judgments. There are also rules for types themselves, for constructing the types. So in the same way that we have the syntax of the language and then how the language works, completely analogously, there will be a syntax for the types, which are just going to be because how the type's control computation is built into the judgment rules. So the judgment rules are a bit like the operational semantics, not quite the same, but a bit like them. And then and they, in the same way that the operational semantics are specified in terms of the structure or syntax of the programs, the type judgment rules will be specified in terms of the structure of the types as well as the structure of the programs. So we can kind of see the different kinds of the structure of types as well as we're going along. So I don't have to kind of do them separately as long as we understand that they can be independently specified. Hopefully that made sense. Did that make sense? Did you follow what I was driving at?
Not totally, but
okay.
Maybe it'll come together if we do an example.
Yeah. Okay. So let's take a look. Let's go really slowly and carefully, just so that we all get on the same page. All right. So the judgment. So remember, our programs have kind of round braces and squirrely braces. And what we're saying is, if a term or an expression inside the round brace is typed A, and the remainder of the terms are typed gamma, so there'll be like a T1, and that'll be typed A1, and a T2 is typed A2, etc., and those are all inside gamma. So this is just like, you know, typing the parameters of a function, right? And then inside, you've got some constraints that you're going to satisfy inside the squirrely braces. And over here, you have so you were able to successfully type this program this way, and you've successfully typed this program this way, so that the head of the stuff in the round braces is typed B, and then the remainder of the stuff in the round braces is captured by delta, and then these are the constraints that you're going to satisfy in this program. Then you can make a new program in which you bundle these two expressions together and typed it A tensor B. So this type says, you know, whatever the behavior of T is, it's going to be isolated from the behavior of you. That's essentially what's going on, and we just simply put the two sets of constraints together. That's all that's going on. And the reason we know we can do that is because these are going to be in a namespace that's entirely separate from these, so they won't interact. And that's what essentially makes this rule safe as a typing rule.
What part says the namespaces are separated?
So the part that says the namespaces are separated is the fact that to get this type judgment, you utilize completely different resources than the ones to get this type judgment. So the gamma and delta don't mention the same resources. So since gamma and delta don't mention the same resources, these guys, these constraints, can't involve the resources between the two, and so it's perfectly safe to mix them. Oh, did we lose you, Vitalik? Vitalik, are you there? Okay. Oh, are you muted? No? Hello? Is anybody there? Okay.
I'm still here.
Okay, cool. All right. I just want to make sure that everyone is here and that we're kind of covering that material quickly. All right. So did that answer your question, Martin?
Yeah, I got it.
Okay, cool. So then it's with par. What you're saying is that effectively they're connected. So you're saying that T is typed A, and U is typed B, and then you have gamma, which are some remaining typed assignments, and then you've got some constraints that are that the program requires in order to execute, or that is going to be the execution of the program, really. So then from this judgment, you can bundle T together, which is really a kind of connection, and you give it that this is par, that T and U are somehow connected, and what the connection really is basically all of these constraints, or some subset of these constraints is the kind of fat pipe between T and U. So if you remember, the constraints up here, the TXNs, the transactions, they're really wiring up things. Oh boy. Oh, but you were on before. Okay, so that's weird. Hold on a second. Oh no. So let's see. It looks like Vitalik got jumped, but he was in the call before. Let's see. I mean, one thing we could do is just completely turn off the audio and use Skype as the audio.
Skype audio doesn't work for me.
Oh, of course. That's weird. Can see the others there. Huh. And everyone can hear. Let me ask Vitalik what browser he's using.
I got a feeling the problem's gonna be more related to internet in China.
Yeah. Jeff, Jeff, you're really, really distorted.
Jeff, you sound like a robot. Still sound like a robot.
Um, let's see. I mean, I could try. All right. Well, we'll just continue, and then we'll circle back next week on any stuff that people want to get. Okay. So, and then Vitalik can also watch this later. Okay. So essentially, each individual transaction is like a kind of wire, and then so the par is essentially suggesting that there's a kind of there's a bunch of these transactions that make a fat pipe, and that's what this par is. So this is isolation, this is connection, and then what we have is that under the assumption that P and Q are well formed, so they're well typed this way. So you've got there's a T. Oh, that's interesting. I've used G's here. They should be turned into gammas. That's a typo. I should fix that. There's a T is typed A, and then the remainder of these the remainder of the head of this program term is typed with a so it's like, you know, sequence T, sequence G. So you think of it as T1 type G1, T2 type G2, etc. And maybe these should, yeah, that's right. And then the U is typed B. But now here's the important thing, that the U's are typed the remainder of the head over here is typed exactly the same way as the head over here. Okay, so the only difference between these two round braces is right at the head. And then you can form a menu or choice, which will bind these variables, these fresh variables x, to these types here, right? So you'll make an assignment saying that, you know, x1 is of type G1, x2 is of type G2, etc. And then you freeze P and Q, and you say that's of type A and B, meaning that you have a menu of possible options here. And then you now remember, this choose part here is an entire term, and that's in the head position of the term that is constructed, right? And then the remainder of these variables are now exposed in this term here. So x1, x2, x3, and each of them is typed G1, G2 respectively. And then there are no constraints in this term, because all the constraints are frozen up in P and Q. If you have a program which is typed T with A, the head of the stuff in the round braces. So I'm gonna with that. Hopefully, it won't be too confusing. I'll call these parameters and these constraints. These are a little bit more than parameters, right? Because there's both output as well as input, and the output and input are structured. But hopefully, without too much confusion, we'll call this the parameters. So if the parameter in the head position is typed A, and then whatever the remainders are typed, then we can say in left of that term is typed A plus B for any B, right? And because T is in the left part, and then we can type if U is typed B, then we can type in right is A plus B because U is in the right part, right? So all that's doing is saying it's a kind of selection, and so what will happen is a selection will be mapped, will be cut against a menu, and in left will take P, and in right will take Q, as we saw in these rules here. Right, so choose wired up to an in left causes the choice of the P, whereas choose wired up to the in right causes the choice of the Q. So we went through that last time. And then here's where we get real namespace development, right? So if you look at contraction, this is kind of the interesting one. If you have T typed store A and U typed store A, so they're both a form of storage, then they both use the same sets of type judgments, and you have just one set of constraints, then you get that T contracted with U is of type store A. Likewise, if you do replication, then if you have that T is of type A, and then you've got this sequence of T's, and then you have gamma. So here, the reason we're calling these out is because we need to make sure that the X's are typed in the same way that the terms they represent are typed. Okay, then so that's what gives you the so what you'll get is a freezing of the term, right? So replication freezes this and then makes with the X's at the head. So the X's are going to line up with these T's, right? And then the X here will now be made available at the top level of this term. So essentially, it's just careful controlling of the term formation with respect to the namespace. That's all that's going on in these typed type judgments. And the way the namespace is really controlled, if you look carefully, is just in the resources that are required to construct a new program. And so most of it has to do with exactly how the resources are connected to computation. So here the resources are connected to it's a real connection. The same set of resources are so gamma and the transactions are necessary to create the hash between T and U. So this is kind of like an externalized form of the transactions, and it's a fat version. Go ahead.
So the namespace is created from the resources that the computation is using.
The namespace is in tight correspondence with the resources that are being utilized. Right. So whenever we do a tensor, right, the resources that are here are separated from the resources here, and the types tell us that. Whenever we do a par or a kind of connection, then the resources are connected. They're wired together. And notice that like Jack Peterson sent me a Slack question about the difference between par and width. Notice that the gamma here is a bunch of different, so there might be a U1 and a T1, and each of those are typed, A1 and B1, or B1 and A1 respectively. So those live inside here. Here we're actually insisting so that the types remain the same, but the terms are different, right? So here the terms and the types are exactly the same. Here the types remain the same, but the terms can be different, right? The T's and the U's can be different. Mm-hmm. And so it's only at the type level that we form the menu choice. Is that helping answer your question?
Yeah, I was just trying to think more about the nature of the namespace.
Yeah, so what I'm trying to suggest is that whenever you have so let's look at the possible resources. So the resources are all in some sense in the round braces, except that the constraints constrain how the resources are used internally, right? So these are the cuts or the wirings of the resources together, the thing that will create the exchange. So what happens here is that whatever names are utilized here will be separate from the names utilized here. That's the requirement of the hypothesis to get this type judgment. You can't share any names. Otherwise, there would be some overlap between gamma and delta, and it's required that they be separate. So whether you do that by insisting that they don't intersect, or by or alternatively by simply injecting them into separate namespaces, it doesn't matter. The requirement, and Abramsky is quite clear in his paper, right? You're doing a kind of injection. So the namespace is growing, and we looked at the ways that the namespace grows via our exegesis of the copy rule last time, right? So x left and x right grow the namespace. Is that making sense?
Oh yeah, I'm quite comfortable with namespaces growing.
Okay, cool. All right, so if you kind of stare at these rules for a bit, what you start to realize is that all that's happening is wiring up the terms in such a way that the types are enforcing either namespace separation, as in this rule, or namespace connection, as in this rule. And then the big difference between the additives versus the multiplicatives is that these guys are going to they only worry about resources at the type level, and they insist that the types are the same, but the terms may be different, right? And whereas here it's terms and types, and so really this is par is doing shared resources. This is not shared resources, but same types, and that's the difference. Isolated resources, shared resources, and this is same types, potentially different resources. And then we looked last time at the weakening, contraction, disposal, and replication, but all the types follow exactly the operational semantics that we looked at last time. So unless there's a need to go over that, we don't have to. The only other thing that we didn't look at was the axiom rule. So the axiom rule is if you remember, we said that this was like the identity. This was like the identity. In point of fact, you have to be. You know, I wrote a I wrote a wire in here, but that wire effectively disappears. So what this does, this requires, since it's X in both places, what comes in goes out, or depending on how you interpret the polarity, what comes in goes out. So you don't need to write that constraint down here that X equals X, because transaction XX evaporates as one of the reduction rules. So this is so the most basic well-typed program is identity. What comes in goes out, and that's how all of this gets off the ground. So over here you'll notice, and I was hoping someone would say, hey, wait a minute, you know, all of these have hypotheses, right? All of these rules have hypotheses. So how do you ever get this thing off the ground? Where's your type judgment that allows you to just start something, right? And here's the type judgment that allows you to you know, begin with a program. And you know, this is sort of your most basic program. So if we were to treat if we were to say that our ground types included the type of Satoshi, so which I'll write as a capital S, right? Then we can write down some basic programs from here, and then explore the rules. All right, so let's take a look at that. Maybe I'll write it in the Casper channel. So we know that X being typed 1 Satoshi, and so I'll write this as tilde S because I don't have a LaTeX plugin in Skype. Okay, so there's no constraints on this. So instead of the S perp, which is what we would have here, I'm writing tilde S to have an ASCII symbol for it. And hopefully that helps you understand that the perp symbol is like a kind of logical negation. So it's relating input to negation and positivity to output. So we know that that's a well-typed program. We also know that if we were just to pick a different variable, something that was distinct from X, and now instead of using Satoshis, how about I use E for ether? That's also a well-typed program. And in fact, to state that these are well-typed, what I'll do is I'll put the little turnstile there, and that is the indication that we've done the type judgment, and in fact it is correct. So this little turnstile is the indication of, yeah, we've checked the types, right? So now that we have two well-typed programs, let's see if we can apply the tensor rule. All right, so I've got something like this, and I've got something like this, then I should be able to form something like this. And the important thing is that T is distinct from U, A is distinct from B, distinct in a certain way, meaning they're separate copies, right? They're not identical copies. So then what can we get? Well, we ought to be able to get, as a conclusion of the rule, here I'll move this over so we can see the rule and the typing at the same time. As a conclusion of the rule, we ought to be able to get that X tensor Y is of type tilde S And I'm just going to write the star again instead of the funny cross because I don't have a LaTeX plugin. E, and we have the remainder of the type judgments. So what are those type judgments? Well, that's X, S, and Y, E, right? So the head and the rest, the head and the rest. So if X colon tilde S is the head, then X colon S is the gamma here. And similarly, if Y colon tilde E is the head, then Y colon E is the delta here. And so then I get both of those copied down. The gamma and the delta get copied down, the X and the Y, and then I just put the constraints together, but the constraints are empty. Right? So we get that. Likewise, we also get, oops, that's weird. Let me edit this. Looks like there's some kind of...
It's because of the two multiply signs that turned it into bold.
Rightio. Let's see. I wonder if I put a slash here. Wow. Nope, that doesn't help.
Yeah, I don't know how to do that. I tried to figure that out too one day.
Okay, so what I'll do is I'll switch it to a circle. Not my favorite choice, but I'm not seeing an option that's quick and easy. Unbelievable. Seriously? What does circle mean? Wow. Okay. One other option. Oh, is that the tilde? Is tilde giving me the line through? Wow. Okay, I can't use bang. Bang is also used for negation. Humph. I'll use carrot, I guess. Again, not my favorite one, not my favorite choice. And hopefully this doesn't trigger some other edit. Okay, there we go. So then I'll be consistent here. Okay, so those are so that's one program. Actually, if you look, I'm going to flip it around because it becomes an awfully much easier to see. So what I'll do is I'm gonna rewrite this one last time. And we're totally allowed to do this. If you look at the rules, this is absolutely the same. But I'm just going to take the carrot and move it over here. And I'm going to do the same here. I'm going to take the carrot and move it to the right. So flipping parameter order is okay as long as you keep track of it carefully. And then, so then this becomes that, and this becomes that. Okay, and now what's interesting is we're free, if we flip it round again, so that we make the left-hand side be the head of this term be the gamma. All right, so I'm just going to rewrite this by reordering this carefully. Oops. Okay, so so this is our gamma. X is our T. Tilde S is our A. Y is our U, and tilde E is our B. Then we are allowed to apply the pi rule. I mean the par rule. Okay, so then from here we can conclude that the following is well typed: that X hash Y is of type, and I'll just use the hash for the types as well, hash E, like that. And if you understand what's going on here, what this says logically is that there's a relationship between par and tensor. That par is effectively the negation of the tensor. So remember that what's on the left side in the axiom format, what's on the left should be the negation of what's on the right. Don't do that. So what we have is that at a higher level than just variables, what's on the left here should be the negation of what's on the right here. So what we're saying is that the caret, logically, the caret of S tensor E should be equal to the caret of the S hash the caret of the E. And that is, in fact, a logical theorem in linear logic. In fact, you can define par in terms of tensor and the negation. So the type judgments correspond to the theory, to the logical theory of linear logic, and the programs are providing computational witnesses that verify these logical theorems. So that's that's quite pleasant, right? In the sense that what we will discover as so if we have a theorem prover that allows us to prove theorems like this, that will be in alignment with what the type judgment believes is well typed. And in fact, the proofs that prove these theorems can be turned into linear programs, right? And so that begins to tease out for us the relationship between the type checking and theorem proving. So there's a close correspondence between the type checking and the theorem proving that is, and that correspondence is often called the Curry-Howard correspondence. But this is why I was saying, so once you have types that can do things like control the namespace, then the type, then proving that or running a type check is equivalent to showing that the programs are well behaved with respect to the sharding requirements. In addition, one of the things that we can figure out, or one of the things we can determine, is that the types when a program is well typed, the program will terminate. There are lots of non-terminating programs in this programming language, but the ones that are well typed must terminate. So that's another way to get at some of these complex behavior.
So you can't have an equivalent of a recursive type.
There are recursive types, absolutely, but
If you have a self-referential recursive type, then like it wouldn't terminate.
Only, but the kinds of types that we have here, the way the recursion is managed is carefully done through the bangs and the questions, and that's the only kind of recursion that you can get. So the only kind of recursion that you ever get is loops with a base case or an exit condition. So what you'll get are essentially menus where one option is the recursion terminates and the other option is keep going. And that's effectively the strength of the recursion. And you'll be able to show, and in fact that's part of the proof in Abramsky's paper, Computational Interpretations of Linear Logic, is to show that that the complexity keeps reducing and reducing and reducing until eventually you take the exit branch.
Okay.
Yeah. So it's actually much more interesting and much more subtle than one might think. There are lots and lots of situations where you can tame expressiveness. I'm kind of guessing, I don't remember off the top of my head, but my guess is that well-typed proofs like this are of the computational expressiveness of context-free languages. So it's not going to be Turing complete, but it will be effectively it can detect balanced parens. So if you remember back to our discussion 2 times ago, where we talked about open round brace, close round brace, open square brace, closed square brace, and what that can do for sessions. That's essentially what's going on here. These are fancy ways of checking that your parens are balanced, and checking that nested parens are balanced is basically managing session state. So that's kind of cool, right? Because that's effectively the kind of semantics that you wanted out of the Ethereum virtual machine. But here, we can give you that without limiting the kind of parallelism that you can have. And that's super, super important, right? It's really crucial that you have, in order to have real concurrency and all the advantages of concurrency, which means that some computations are happening at the same time and they're not mucking with each other, or exactly the points where they do have to synchronize, and so what the timing advantages can be to let some parts of the computation run simultaneously with others. So that is what's necessary. Those are the semantics that I've argued with you guys are necessary to get performance. You don't have to have this global sequentialization, and you can get safe behavior by carefully constructing type systems that encode the semantics that you want. And an example, of course, is this management of session state. And here we can go even better, because we're saying that the management of the session state is related to sharding along the namespace. Right. So that gives you an even more powerful thing, because now you're.
When you're saying sharding along the namespace, are you talking about the same thing I was trying to describe with the ambience, like
yes,
ambient and breaking it off into a new shard?
Yes, exactly. But that's your intuitions were spot on. I wouldn't align that with ambience in quite the way you did, right? So I read through the paper over the weekend, and the main insight of Luca and Andy, so that's Luca Cardelli and Andy Gordon, is that you can do this kind of whole tree rewrite. So if you look carefully at the pi, if you compare the pi calculus, here's the way to say it. pi calculus is to lambda calculus as ambient calculus is to x. And so far there isn't a good x that fits that box. And the reason is because if you look at the way lambda calculus does things, it does things by data transfer along a parameter slot, right? So it's like the function has a slot where it needs some data. The parameter or the value that the function is being applied to is going to eventually evaluate and provide a value that goes into that parameter slot, right? And we know like how to do that with stack discipline, right? So you push the function, you evaluate the parameter, then you pop the function and and hand it the parameter, right? So that's that's a really time-honored tradition. There are lots of different parameter passing strategies for stack-based machines, right? But all of them have to do with effectively establishing a channel between the parameter and the function, and so all the pi calculus is doing is to generalize that and say, well, we're just going to say that there is a channel between the thing that provides the value and the thing that needs the value. And so they don't have to come together in a stack. They can be all over the network, and as long as they have a channel between them, then they will eventually communicate. Now the ambient calculus is completely different. It's like rewriting the whole tree structure of the program. It's the reduction strategy of the ambient calculus for in and out and dissolve are taking the structure, taking the nesting of expressions inside a program and changing their nesting relationship.
Right.
That's not the same at all as supplying a parameter value, and that's why it's been very, very challenging to say what is how to give a fully abstract encoding of the ambient calculus into the pi calculus. So far, that doesn't exist, or to the best of my knowledge, that doesn't exist, and this certainly didn't exist as late as 2007. So maybe in the intervening 8 years, someone's come up with one, but I haven't heard of it. Now, I think what you're doing is, even though you have some program mobility, it's not quite the same as what the ambients are doing.
It's definitely not the same.
Yeah, exactly. So I think that the intuition that you have is very similar to the intuitions we've been discussing, which is that if you simply say that names have internal structure, so names are like paths, and which means that a channel is a path.
Well, no, I think I separate channels from names. Names only exist in namespaces. Oh, yeah, but a channel can be part of a path.
Right, exactly, and right, and so what I'm trying to do is to get a more abstract characterization. So in Milner, there is no channels and names are the same thing, right? So in the pi calculus, channels and names are exactly the same. They're just synonyms for the same idea.
Mm-hmm.
And the pi calculus is parametric in what a channel is. It doesn't say what a channel is. It says what it says is things that channels have to so when we talk about channel space, we're talking about namespace. So what he says is that the namespace as a whole has to satisfy 3 properties. So one property is you have to be able to compare channels for equality. That's a requirement. Mm-hmm. So for example, if you said that channels were programs, you might have an interesting problem, right? Because comparing programs for equality can lead you into halting hard problems. So that's an interesting challenge for anything that wants programs to be channels unless somehow you can tame that issue, like we did here with this type system. Okay, so the second requirement of the namespace as a whole is that it be at least countably infinite.
Infinitesimal.
No, infinite.
Right?
Infinite.
Well,
So,
I think of it like infinitesimals, though. Like, you know, we have whole numbers, and then we have fractions, and like fractions can keep getting smaller and smaller and smaller forever.
right, but the difference between so fractions are the rational numbers, and the rational numbers, at least with respect to cardinality, have exactly the same cardinality as the counting numbers.
Yep.
It plays a 1-to-1, and that cardinality is the only cardinality required for the namespace. So it doesn't. It's not required to be uncountably infinite. For example, you could do that, but that's not a requirement that Milner places. It's just that for any collection of names that you've always got to be able to pick one that is fresh and distinct from all of those.
Right. But the weird thing with ambients are, since they can be nested, it also implies the namespace has an up and down.
Right, and so this is what I was trying to suggest, is that let me just complete the thought. So Milner requires 3 things. One is you can compare names. 2 is that you have at least countably many of them. The third one is the weird one. The third one is he doesn't insist on any internal structure to names. So he doesn't, require that names have any structure at all. In fact, in private conversations, Robin and I argued about this, right? So his concern was that as soon as names had structure, like even if they were like numbers.
Like structure, you just mean like file systems in Unix type of structure.
No, it could be as simple as the structure of counting numbers.
Ah, okay.
Counting numbers have all kinds of interesting structure, right?
Yeah.
So some of them are prime, for example. Some of them factor. So that's interior structure. So Robin was concerned that if you insisted on any structure to names, that it would lead to pointer arithmetic, because names effectively become pointers in the pi calculus. And so if you have a structure on names, then you could do pointer arithmetic, and that's really, really hard to control, right? Like if you've ever seen people doing clever pointer arithmetic in C programs, that's really, really challenging.
Sure, yeah.
Yeah. Okay. So to debug, and he wanted to not do that, but he actually recanted from that position in a paper, an obscure paper called Naming Monoids, and I think I've got it here somewhere. No. Maybe it's over here. Oh. I know I've got it up. Hang on a second. I didn't mean to do that. Darn it. Maybe. Okay, so not that one. Here it is. Yeah, so in naming monoids, he actually identifies the monoidal structure required of names. And then, having identified the monoidal structure required of names, the next thing he does is to find some names that some examples of naming monoids that have all the properties. And the most paradigmatic example is paths. And this is completely unsurprising, because paths are a content addressing scheme that is, works at internet scale. Right? right? I mean, so
Yeah.
so I mean, it's like, why you might as well just go with the flow here. So if you make names be paths, then you automatically have up and down. You automatically have region control. So you get you get all of the behavior that you want in terms of having nested domains, simply by having nested names that are paths. And that's effectively what Abramsky is doing here in his proof expressions. And by the way, this little programming language is just a complete and utter recapitulation, total ripoff, mix up and mash up of computational interpretations of linear logic. So this little contracting language is nothing other than proof expressions recast for the blockchain. So remember when we looked here, the x left and x right is simply adding another element onto the path. And so this is the bridge that gets you the kind of nesting structure that you wanted, but not the whole cloth, tree rewrite of the program structure, because that not only is that harder to interpret when you're talking about programs that are moving around on the internet, but it also turns out to be too expressive. In the ambient calculus, you can do leader election in one line, or well, depending on where you do your line breaks, maybe 2 lines. But it's so leader election is something that the entire proof of work mechanism. Like if you look at Bitcoin in G, right? Effectively it's using proof of work to do leader election, and that's it, right? And then the leader publishes the block. So the same thing, you can implement all of proof of work in a one-line ambient program. That's too expressive. That's not what people would allow to run. They won't sprinkle nodes like that all over the internet, because it means that the possibility of doing bad things on the other side of a firewall is too great.
So what do you mean by tree rewrite exactly?
So the program tree itself, instead of just like substituting in certain slots in the tree, which is what beta reduction does, right? So imagine you take the abstract syntax tree of some contract. Okay. Okay. Beta reduction is all it does is wherever you've mentioned a particular variable, it changes the program text to mention the value instead. That's it. You're not changing the structure of the program. You're just changing, positions in the tree to be values instead of variables. Okay.
So let me clarify what I was thinking here. So with ambience, I wasn't actually thinking of using. I wasn't thinking about ambient calculus as the base computation. Like I would assume what's inside of ambient and what's being computed in ambient is like EVM or WebAssembly or something. The only ambient calculus that's going on is sort of how the different ambients interact with each other.
Exactly.
How the shards and stuff run.
Yeah, exactly. And now you're arguing even more in favor of the position I was trying to communicate, which is that it's not ambience that you're going after, but rather you have path-based namespace. Okay. Yeah, and in which case we're now completely in sync. We're on the exact same page. And so what I've been arguing is that if there's a set of relationships. The relationship is between sharding the names versus sharding the state versus the locality of computations, right? And all of those things can be viewed as separate. But what I've said is, if you shard the state, that will imply that you've sharded the names, and those two actions will have an impact on locality with respect to where a program runs, because as soon as you've done that, then to access state that's in the same shard is easier than to access state that isn't. Right. Which will happen.
In my mind, it's a very fuzzy locality.
Yeah,
it's
of
not
course.
clear. Yeah. It's the only people that the shards are real for, if you will, are going to be the validators. Everyone else is just going to see one big tree.
Yeah, no, exactly. Yes, exactly. I'm talking about a logical characterization versus a physical characterization. And sometimes, yeah, if you think about this physically, it'll be completely confusing. But if you think about this in terms of the kinds of distinctions that you can make, here's a way to think about it. In topology, sometimes the way we reason about the way we reason about spatial information or locality is in terms of separation axioms. So one of the most common kinds of spaces that we deal with on a regular basis, like the kind of space that we walk through, is considered to be Hausdorff. And what we mean by Hausdorff is, given any 2 points that are distinct, I can find a neighborhood of one, like I can draw a circle around one, that doesn't include the other, and vice versa, I can draw a neighborhood around the circle around the other that doesn't include the one. So that view of space as characterized in terms of these logical properties is the kind of bridge between these worlds, right? So it's not locality in the sense that I lay down a coordinate system. It's locality in terms of these logical separations. And those logical separations are what we're imposing on the namespace by these kinds of type judgments, for example. These kinds of type judgments actually talk about separations in the namespace. And that's what gives you this interesting namespace topology. And that will the next step in that is that will impact performance. So when computation is co-located, sort of in the same namespace with state it needs to access, then things are faster than if it isn't, because if it isn't, it has to go through an intermediary or several intermediaries to gain access. So what that means in terms of this computational model is there are a bunch of transactions, a bunch of TXs that set up a wire of some length between the program and the state that it needs to access.
Okay.
Yeah, and you can actually count it. You can count like if you set up the situation correctly, it will come down to numbers of transactions like this, right? Where you've got an X on to an E1 and an X to an E2, and the movement to access a far state will be that it will be an X and a Y, and the Y is to a U, and the U is to E2, right? And so this will all collapse to the E1 being wired to the E2, but only after going through the X and the Y and the U.
Right. Okay.
Right. All right. So we're way over time, but just to I
wanted to ask you one question. You don't have to answer, but I was curious on is, can ambients have types?
Yes, there are. So I can answer that.
I need types to make everything work, or to make things work nicely.
Yeah. But again, I don't think you need ambience. All you need is a path-based namespace, and then I think you're cooking with gas, and we're like in complete.
Well, I like ambience because it's a nice way to program contracts. If a contract's an ambient and it has subcontracts.
Yes, I totally agree with you there. Contracts should have subcontracts, but that's not making it an ambient. Just because nesting is compositionality. That's not making it an ambient. What makes it an ambient is when the membrane itself is programmable in a certain way.
Exactly.
And that's not what you're doing. What you're doing is you have path-based names.
Well, the membrane is programmable, though.
Okay, so
If you have an ambient and a subambient, like, and you send a message to the subambient through the parent ambient, the parent ambient, like, might have some code to read all the in messages. That code would run before the subambient code is running.
yes, again, that's not ambience.
Oh, okay.
Yeah, so that's a forwarder in the pi calculus, a forwarder and a filterer. What ambience does is it says this code is going to pick up and move inside, like while it's running, the code is going to pick up and move inside this region, and it may make a new region and then invite another code to go into that region, then it will move into that region. And then after they've done some calculations, they may dissolve that region.
Right, I got rid of moving.
Yeah, so that's my point.
Instead, I because it's easier to think about copying and deleting.
Yeah, I understand, but copying, yeah, I think what you're, yeah, we should go through this in more detail. But I think the simplest way to think about this, where you have the fewest moving parts, is that you have path-based namespaces, and you can achieve everything you want by path-based namespaces, and that will enable you to not have to deal with the fact that ambients are way too expressive. Right, because what you're going to have to do is you're going to have to dial back the expressiveness of ambient calculus. Because
right, I've already decided it's not ambient calculus. it's like membranes. It's a simple version of membrane.
Or even less, it's just paths for names.
Well, it's nice to thinking about membranes because messages go through the membrane and trigger some computation for that membrane, and then it might reach the original target.
Right. Well, we should look at we should look at kind of the most bare bones VM, which would be equivalent where we talked about the structured operational semantics.
Mm-hmm.
We should write down a kind of structured operational semantics for the computational notion you have in mind.
Right. I think it's pretty much a bigraph.
Yeah. So again, I would be very, very. Bigraphs are a super general structure about which we have very few off-the-shelf tools. Bigraphs are kind of a way of relating a wide range of computational models.
Right. So I can see it in terms of a bigraph with certain rules.
Well, the rewrite rules of the bigraph correspond to the structured operational semantics. So this is why I'm saying what you want is the next level down in detail. Bigraphs are kind of erasing a bunch of detail, and you want the next level down to make sure that you've nailed down where the computational wrinkles are.
Right.
And bigraphs are kind of erasing all of that to get this higher level view, so that you can relate things like ambience to pi. Right. That was kind of Milner's goal. Was I'll give you an example. Right. So when I worked at Microsoft, one of the things that we did was to build a hardware VM for the pi calculus. And so I worked with Jan Gray and Satnam Singh. And Satnam is now at Google, for example, working on Kubernetes. So Satnam and Jan Gray and Alan Brown and I built a compiler from the pi calculus onto an FPGA. And then Satnam was because he was really sensitive to these kinds of things. He was careful to arrange it so that the little chip, the PyCalculus chip that we were creating, could be tiled over the surface of the FPGA. So giving you lots and lots of Pi machines. And what this raises is something that's really quite challenging, which is how do you distribute the work, the incoming work, to the different Pi machines, right? So this is exactly the sharding issue, right?
Yeah.
Right, and so there you might want to look at some kind of ambient Pi combination. But even there, a simpler approach, and so that's why bigraphs are useful, right? Because you want to look at some combination of calculi. And so in order to understand the behavior of the whole system, like all these Pi machines tiled over a single FPGA, you want to look, and so you want to look at the whole system and see if it behaves correctly for a given stream of work. A much simpler approach, and this is kind of what I began to understand. Like we did that work back in 2004, right? It's now 2016, so 12 years ago. And in the intervening 12 years, I've become much more convinced that if you an intermediate step is just to have names with a certain amount of structure, and that structure is what enables you to control distribution characteristics.
Okay. Yeah, as long as you can, if you're going down a path, can trigger different computation along the way before you reach the destination.
Absolutely. Yeah, totally. Yeah, that's it's necessary and important. And in fact, I can write down for you in the operational semantics side what that looks like. But we should do that maybe next time. So yeah, I mean, I think we're definitely making progress here. We're starting to have world views line up.
Well, that's great.
Yeah. All right. So then next time. I hope everyone. And I think this time still works for everyone.
Yeah.
Okay.
All right. Sorry for dragging it over.
Yeah, no worries. And thanks for joining, Jeff. Hopefully we're awfully quiet. Hopefully this was useful.
Yeah.
Yeah, we didn't get any of that. The audio was this robot quality. All right. Talk to you guys later. Ciao.
Bye.